All right, so this video is our Math 1050 looking into the book as section 5.1 and 5.2, which are both going over systems of linear equations. So we're still talking on the subject of linear here, and we know that that means that the variables are to the first power. So what's going to be new in these sections is that we're going to be looking at what is a system. We want to define that. And then we also want to talk about, or it's going to be important to identify how many variables there are. And what does the solution to a system mean or look like graphically? We're going to look at the substitution method for solving. Substitution, sorry. And we're going to look at the elimination method. Which, if I'm completely honest with you guys, this is my favorite method. Substitution works in only certain situations, so that's why the substitution method isn't one of my favorites. Then finally, we're going to be talking about when different categories of solutions. Okay, so before we can even do these two sections, we have to know what is a system. So a system of equations, or a system in math, is more than one equation. So in the case of a system of linear equations, we're talking about more than one equation that has more than one variable. This is where we talk about how many variables there are. In order to completely solve a system of equations and get a singular answer, the number of equations has to equal the number of variables. Otherwise, we're not going to be able to get a singular answer or singular solution, and we'll talk more about what that means. But when we're talking about the number of variables, or how I brought that up in the last slide, that's what it means, is that you want to be able to make sure that those two things are equivalent to each other. So the solution of a system of equations is the point of intersection on the graph. So if we think about the linear equations that we're used to, two variable, usually x and y, we know that that graphs as two lines. So if we think of our graph as an xy coordinate plane, here's x and here's y, and when we graph two equations, so there's our first equation, here's our second equation, the solution to this system is actually this point of intersection, whatever that xy value is right there. So that's why I was talking about singular, is that in order to get one point of intersection, we have to have at least, or two equations to be able to find that point of intersection. If there are three equations, and they're two variable equations, in order to get a singular answer, they all have to have that point of intersection in common. All right, so the substitution method for solving a system of linear equations has to be written in a very specific way. One of the equations or both the equations have to be written in a specific way. So what I mean by that is at least at least one of the equations has to be solved for a variable. And so what I mean by that is we could have a linear equation written in standard form like 2x plus 7y is equal to 18. Then the other equation could be written as x is equal to 4y minus 3. So what we know is that these two x's, if we're looking at the point of intersection, these two x's have to be equal to each other, which means that this x also has to equal 4y minus 3. So we take this expression and we substitute it in for x, and that's the substitution method. So now it becomes 2 times 4y minus 3 plus 7y is equal to 18, and then we solve this equation for y. And then what we can do is we can take this answer and we can plug it into this equation right here, and we can solve for x. And so our solution to this system is the coordinate point 17/5 and 8/5. And that's how you would solve using the substitution method. Once again, an equation might start out in standard form and you can rewrite it in solving for one of the variables and then substitute in. But I would really only recommend the substitution method if it's already like solved for, and you can save yourself a step of solving for the variable. And that's what the substitution method is. So the elimination method for solving a system of equations is when one of the equations isn't solved for one of the variables. So particularly if they're both written in standard form, but it could be written where the variables are on both sides as well, and you can still do the elimination method. So basically, when we say eliminate, we mean that we are going to combine the two equations. So combine like terms. Equations, or we do the elimination method with two equations. We could go use that, but to go to a bigger system, but usually we just start two equations at a time to be able to start eliminating things. So you combined two equations to be able to cancel out, for lack of a better word, or to make it equal to 0, to zero it out. So what I'm talking about here is, we'll start simple. Let's just say we have x plus y is equal to 5, and then 3x minus y is equal to 13. So what we can do here is, these are already opposite values, so when I combine them, they're going to cancel each other out, or they're going to equal 0. So we're going to go ahead and add these two equations, and we get 4x is equal to 18. And we can divide by 4, and we get x is equal to 18/4, or 9/2. And then we can substitute that back into one of these other equations to be able to solve for y. And so we know that our solution, our point of intersection, is 9/2, 1/2. So the whole goal, like I said, to eliminate is when we combine the two equations, we can cancel out a variable, which means we need to be able to get opposite values. So if we keep this in mind, we might have a system of equations where we don't start out with opposite values, so we can do some math to be able to get that. So let's say we have 4x minus 3y is equal to 20, and then let's say that we have x plus 2y is equal to 8. All right, so what we can do is we can either get opposite values with the x's, and so we could get plus or minus 4 if we wanted to, or any other opposite value, or we can get opposite values with the y and just try to get positive and negative. I'm going to go with trying to get plus or minus 4 because this bottom equation, all I have to do is multiply that by negative 4 to get that value, to get the opposite of 4x. So we have, once we do this, we've got 4x minus 3y is equal to 20. And then we got negative 4x minus 8y is equal to negative 32. And now I can combine the two equations and eliminate x, because that equals 0. And so then we combine the rest of it, and we get negative 11y is equal to negative 12. And then we can divide by negative 11, and we get y is equal to 12 elevenths. And then we can substitute that into one of the original equations to be able to solve for x. And then we find our point of intersection. So the most difficult thing with the elimination method, honestly, is trying to figuring out what you can multiply one equation by or both equations by to be able to get opposite values. So honestly, as long as you get opposite values, it doesn't matter. That's your big goal, to be able to do the elimination method, and then it's super easy from there. So 5.2 goes into 3 variables and 3 equations, and what does that look like? So first thing that you need to know when we talk about graphically what this is looking like, a 3 variable equation is graphed on 3 axes, or it's has 3D, 3 dimensions to it. And so it's really actually a graph in space. So when you graph a 3 variable equation, it is a 2 variable or 2-dimensional surface. So we're really looking at the point of intersections of planes. So like if I have a flat surface that's going this way, and then I have one it's hard to draw in 3 dimension, and then I have one that's coming along here, and then comes over, and then I've got one that's coming through here. This line that they intersect at right here is the solution. So a solution to a point of intersection can be a line for 3 variables. So it's not singular, it's non-singular, or it can be one point of intersection where they all have this one point in common, where 3 planes all intersect each other. So for example, this would be a point of intersection when we have all 3 axes intersecting each other, and that would be a singular solution. So I'm going to just write a system and then show you how you would solve it using the elimination method. Okay, so the rule of thumb when you're doing the elimination method is you want to be able to go from 3 equations to 2 equations to 1 equation where it's 1 variable and you got it solved for. So we're going to look at this and we're going to figure out, okay, what variable can I eliminate? Well, if you notice in equation 1 and 2, they have opposite z values. So we're going to go ahead and eliminate z by combining these 2 equations. And so 2x minus x gives us x. Negative y plus 5y gives us 4y. These cancel each other out, and we got 16. So now what we want to do is we're going to combine two other equations. We can't combine the same two, and we're trying to get another two-variable equation with just x and y. So we got to get rid of z again. So we have to use the third equation because we haven't used it so far. So what I want to do is, because I have negative 3, I'm going to take this first equation and I'm going to multiply it by 3 so that I get a positive 3z. So now we have 6x minus 3y plus 3z is equal to 18, and then we still have 3x plus y minus 3z is equal to 12, and we do the elimination method again. So we got 9x minus 2y is equal to, because this equals 0, is equal to 30. So now here's our two variable equations, and we're going to do the elimination method. So we've done it twice already. We've got to do 3 eliminations when these equations are written in standard form. So we're going to do the elimination method again, and you can see that we have 4y and we have negative 2y. So we're going to take this red equation and we're going to multiply it by 2, so we get negative 4y. So we've got 18x minus 4y is equal to 60. And we're going to go ahead and do the elimination method again. Those cancel each other out. And so we have 19x is equal to 76. Divide by 19. And we get x is equal to 4. So from this point, we're going to start working back up, and we're going to take x equals 4, plug it into one of our two variable equations, and solve for y. One of these two variable equations. And we're going to solve for y, and then we're going to plug that into one of our three variable equations and solve for z. So I'm going to take 4, and I'm going to plug it into x plus 4y equals 16. So 4 plus 4y is equal to 16. And I'm going to solve for y. 1 plus y is equal to 4. Sorry, I did that a little different. I divided everything by 4. And so y is equal to 3. And now I'm going to plug that into one of my three variable equations. So I'm going to plug it into the first one. So 2 times 4 minus 3 plus z, because we don't know what z is yet, is equal to 6. We got 8 minus 3 plus z is equal to 6. So 5 plus z equals 6, and z equals 1. So then our point of intersection, or our singular solution, is 4, 3, 1. Then we can write it in our set brackets. And remember, this is our x, y, z, so it goes in alphabetical order when you write an ordered triple. So there's 3 numbers, so it's 2 numbers is an ordered pair, 3 numbers is an ordered triple. Okay, so let's talk about the categories of solutions. So we already talked about a singular solution, which just basically means that there's one unique solution, and that means that one unique solution is and that means it's either an ordered pair / triple / however many variables are, but basically it's a point of intersection. The next category is that a solution to a system can be inconsistent. And if you remember, inconsistent, if you think about this logically, inconsistent means that it doesn't match up. And if it's not going to match up, it's not going to intersect. And so this is where there is no solution to the solution to the system, which means that we're talking about parallel lines or parallel planes. slash planes, depending on how many variables we're talking about. It's just that what we're graphing is parallel and they never touch each other. So they're inconsistent. They don't have anything in common. All right. The third category is a dependent solution. If you think about it, dependent, they are what one does, the other one has to do, and they have to connect with each other. They're not independent or their own lines that are together. So what this means is that we're talking about that they, in the terms of a two-variable system, they're the same line, which means there are infinite number of solutions. Which means that two-variable when you graph it, they're the same line. When you were talking about three-variable, they intersect at a line. So there's not one point that they have in common. It's an entire line that they have in common. So there's not just one unique solution, but there's infinite number of solutions, and that's what we call a dependent solution. Okay, if you started out feeling really good about the system and you're like, oh, this two-variable stuff, yeah, I remember to do that, that's great. And that is really our ultimate goal, is what we want to practice, being able to do elimination and substitution with two-variable systems. But if you're feeling overwhelmed by the whole idea of three variables, we're going to practice it once, and it's just to get you an idea and an appreciation for what happens. But there's actually going to be a better shortcut in what we do when we start the chapter 6 section for this linear unit. So if you're feeling overwhelmed, know that there's a light at the end of the tunnel that's going to make things better, or make things easier or better to understand or to deal with. Always the goal in math is to be able to come up with more efficient strategies or shortcuts to be able to do things, and that's what we're looking at eventually. So hopefully this helps, and a good review of the elimination method or reminder of what a subsystem is if you hadn't seen it before. Please make sure that you ask questions and be prepared to still try and work in class and to really understand what we draw from our problems that we work on in class. And I will see you guys later.